This chapter is on friction. We're going to look at the definition of friction, and we introduce it by considering pushing something across the floor, that it takes some force, more force to build up before you can get the thing to budge. So we're going to have two kinds of friction: the friction that's of a static nature, where there is no motion, and then there's the friction where we're moving. That's the kinetic friction or dynamic friction. We'll use the word kinetic for the moving, and we'll move static for the one where there is no motion. And for the static case, it builds up. You push a little bit, you get the friction that opposes you. You push a little more, it opposes you, until you get to a point where it then budges. And then the friction to keep it going is typically less than when you get it to budge. You may have noticed that when you push something, it's a little more effort to push it at the beginning, and then once when it's going, it's not as bad. So we're going to introduce the concept of friction and the coefficient of static friction and the coefficient of kinetic friction, and then we're going to do 10 problems. This is going to be a problem class. The way this course is evolving is that I'm incorporating lots of problems in these last few chapters because we don't really have homework, and this kind of makes up for having homework. We're folding some homework time into the problems, and be sure to work these out on your own. And if you're taking a course in mechanics, you're going to be getting lots of problems assigned for homework and in your book. So we're going to have a workout with 10 problems. I've picked a variety of problems that cover a lot of the basic areas that you'll encounter in courses. And we're a little heavy on the theoretical side, which means that we will work equations out without numbers. You could always put in numbers at the end. So this is a more powerful way to get more, say, bang for your buck, where you work out with symbols the equation first and put the numbers in last, or maybe don't even put the numbers in, just leave the general formula as the final result. So let's get started with friction. Chapter F, friction. The friction chapter. First thing we're going to do is introduce the concept. And to do that, we'll use this figure here. Person's pushing a box and it's sliding on the floor. Now when you push something, it doesn't budge at first. You push some more and it still doesn't budge. Push some more and finally it does budge. And then usually it's easier to keep pushing, sliding across the floor. So this little graph here is showing an idealization where you start out with no force, that you're pushing with no force, then you push a little bit and the resistance, the friction is meeting you, you're still not moving, but then you get to a point where it budges, and then the force you need drops, the frictional force drops. So we have two kinds of friction that we're going to talk about. And the first kind of friction is going to be the static case, where you're not moving. And we basically use a model that's pretty accurate, where the frictional force is proportional to the normal force. That is the force that the floor is pushing up on the object you're trying to move. So for the static case, we pick the proportionality constant to be mu sub s, static friction coefficient, and it's less than or equal to that up until a point when it starts to budge. And then when it budges, you have dynamic, a dynamic situation, we call it the kinetic coefficient of friction. When this happens in kinetic friction, we use K, and that's equal to mu K N. Now, if you went into the laboratory and did some measurements, here you have no force, then you apply a force, and this is the friction. This is basically doing a measure of the static friction, and it's approximately linear. So that means as you increase, in other words, proportional to the normal force. So it's proportional to the normal force. So the force in newtons that you're applied, and then see it drops down. And then real life data is a little complicated, but pretty much approximately constant. So in this case, you would say the force of static friction is mu S N, proportional to the normal force. Let's say less than or equal to that. This is the maximum value up here. And then this, the frictional force of kinetic, is equal to mu K N. And usually the mu K is less than mu S. And usually they're less than 1. So if we look at some values here, aluminum on aluminum, clean and dry. So you have some examples here that are above 1. And if you look at these, most of them are less than 1, and the static values are greater than the kinetic values, typically. So if we go to a case here on an incline like this, then the normal force is going to be acting this way. You're going to have a force that's acting downward. That's going to be mg, and the friction force is going to want to hold you up, the force, say, of friction. So these would be your cases of your forces, the 3 forces. Let's look at the static case again and do a little sketch of a person pushing a mass, and then do a little force diagram. Here you would have normal force going up, mg going down, and say it's a push with P, and this would be the force of static friction going back. So you would have the static friction in this case to be less than or equal to some mu S N. Then if we look at another case here, where you're actually you're moving across the room, then you would have here P, you would have the normal force again, you would have your mg, and this would be the frictional force of kinetic, and the kinetic would be mu K times N. So this is introduction to our chapter, and we're going to do 10 problems with friction.